Right now, millions of kilometers above us, something impossible is happening. An object from beyond our solar system, a visitor that traveled through interstellar space for thousands of years, has just done something no comet, no asteroid, no natural body should be able to do. It's created a giant cross pattern in space. Not a random burst of dust, not a chaotic tail streaming behind it. A cross, two perfectly perpendicular lines extending outward like outstretched arms, each reaching across distances that would swallow planets whole. You need to understand something. Space doesn't do geometry. Nature doesn't draw symbols. When rocks and ice tumble through the cosmos, they leave messy trails, chaotic, unpredictable, following the brutal mathematics of gravity and solar wind. They don't create patterns that look like they were designed. They don't form shapes that make you stop and ask questions. But this object, designated 3I Atlas, has somehow managed to paint a cross in the darkness of space, and nobody can fully explain why. Stay with me. In the next few minutes, we're going to uncover what scientists are discovering about this mysterious cross pattern, why the United Nations just launched a 2-month global tracking campaign focused on this single object, and what it might mean that we're watching something that shouldn't exist, according to our current understanding of how the universe works. This isn't science fiction. This is happening right now. NASA has the images. Independent observatories have confirmed it. The Hubble Space Telescope is currently studying it. The James Webb Space Telescope has turned its instruments toward it. And in a matter of weeks, this visitor will fade beyond our ability to observe it, taking its secrets with it into the depths of interstellar space, possibly forever. Let me be clear about what we're dealing with. This object came from outside our solar system. It passed through the space between stars, survived the cosmic radiation, the absolute cold, the gravitational chaos of entering a new star system. It swung around our sun just weeks ago, and as it did, something changed, something activated. Something began streaming out from it in a pattern that violates every comfortable explanation we have for how comets behave. The cross pattern isn't small. We're not talking about some minor artifact in a photograph or a trick of perspective. The extensions stretch for distances measured in millions of kilometers. If you could stand in space and look at this object, you'd see two distinct lines projecting outward at right angles to each other, perpendicular not just to each other but to the line connecting the object to our sun. Think about that geometry for a moment. Everything about comets, their tails, their jets, their outgassing, is controlled by the sun. Material streams away from the sun-facing side. Tails point away from our star because solar radiation pushes them. That's basic physics. That's what should happen. But 3I Atlas has created extensions that don't follow that rule. They're oriented at right angles to the sun object line, as if something inside this visitor is ejecting material in directions that have nothing to do with solar influence. As if whatever is happening isn't being controlled by the star it's passing but by something else. Something internal, something we don't understand. And here's what makes this moment so critical. We've only confirmed 3 interstellar objects passing through our solar system in all of human history. The first was Oumuamua in 2017, that strange elongated object that accelerated in ways we still debate. The second was 2I, Borisov, in 2019, a more typical comet. And now this one, 3I Atlas, discovered as it approached us, our third visitor, and perhaps the strangest yet. 2 visitors, 2 mysteries, and now with 3I Atlas, we're watching it do something that shouldn't be possible, creating a geometric pattern in space while the entire global scientific community scrambles to gather data before it disappears forever. You might be wondering why you haven't heard more about this. Why isn't this dominating headlines? Why isn't everyone talking about a cross-shaped pattern in space created by an interstellar visitor? Part of the answer is timing. The clearest images of this X pattern only emerged in November through stacked observation data. Scientists are still analyzing what they're seeing. Papers are being written. Debates are happening in research institutions right now. The United Nations initiated its tracking campaign on November 27th, just as this pattern became undeniable. But there's another reason you might not have heard the full story yet. Scientists are careful people. They don't rush to conclusions. They don't sensationalize. When something doesn't fit their models, they first assume the model is incomplete, not that nature is doing something fundamentally different. They look for conventional explanations. They check for observation errors, for artifacts, for misunderstandings. And that's exactly what's happening now with 3I Atlas. Multiple teams are offering different interpretations of what's creating this cross pattern, and those interpretations range from the comfortably natural to the deeply puzzling. Some researchers say it's a high-velocity phenomenon material being ejected so fast from a rapidly rotating nucleus that it creates these perpendicular structures through complex dynamics we're still mapping. Others point to the way images are stacked over time, suggesting what we're seeing might be an artifact of observation methods rather than a real structure in space. These are reasonable scientific positions. They deserve consideration. But here's what's nagging at the edges of this explanation. Other comets don't do this. Other rotating objects with jets and outgassing don't create perfect cross patterns. Something about 3I Atlas is different. And then there's R.V. Loeb. You might know the name. He's the Harvard astrophysicist who suggested Oumuamua might have been an artificial object, a light sail perhaps, something constructed rather than naturally formed. He faced significant criticism for that position. Many of his colleagues thought he was jumping to extraordinary conclusions without sufficient evidence. But Loeb doesn't back down easily, and now he's looking at 3I Atlas with the same unflinching curiosity. He sees those perpendicular extensions, and he asks the question that makes other scientists uncomfortable. What if this isn't entirely natural? What if we're looking at material being ejected in a controlled fashion, following patterns that suggest something more than random outgassing? I'm not here to tell you Loeb is right. I'm not here to tell you he's wrong. What I'm here to tell you is that right now, as you're watching this, humanity is witnessing something unprecedented, and the smartest people on the planet are trying to figure out what it means. We're living through a moment that might be talked about for generations, the time when an object from another star system created a cross in space and we watched it happen. This isn't about fear. Let me make that absolutely clear. 3I Atlas poses no threat to Earth. Its trajectory is well understood. It came close to the Sun, but it's not coming close to us. By the time you're hearing about this, it's already moving away, dimming with each passing day as it heads back into the darkness between stars. The danger isn't physical. The danger is that we might miss something. The danger is that we might not gather enough data before it's gone. The danger is that we might look back in 50 years and realize we had a chance to understand something profound and we let it slip away. So hit that like button right now and drop a comment telling me where you're watching from, because what we're about to explore together matters. This isn't just another space curiosity. This is a question about how much we really understand about the universe we live in. This is about what happens when nature hands us a puzzle that doesn't fit our existing framework. And I want to know, are you seeing what I'm seeing? Are you feeling that same tension between the comfortable explanations and the nagging sense that something deeper is going on here? Let me take you through what we know, what we don't know, and why the geometry of this pattern, that perfect cross shape extending into space, is keeping scientists awake at night, racing to point every available telescope at a visitor that's about to vanish into the cosmic dark. To understand why this cross pattern is so disturbing to astronomers, you first need to understand how comets are supposed to behave. It's not complicated. Actually, it's beautifully simple, which is why what's happening with 3I Atlas is so jarring. When a comet approaches the Sun, the ice in its nucleus starts to warm. Frozen water, frozen carbon dioxide, frozen ammonia, all these substances begin to sublimate, turning directly from solid to gas without passing through a liquid phase. This outgassing creates pressure. Jets of material shoot out from the nucleus, usually from the sun-facing side where the heating is most intense. This material becomes the comet's coma, that fuzzy cloud surrounding the solid core. Then solar radiation and solar wind push this material outward, away from the Sun, creating the classic comet tail. The tail always points away from the Sun. Always. It doesn't matter which direction the comet is traveling. The tail follows one rule: away from the star. Sometimes comets have two tails. One is made of dust, heavier particles that follow the comet's orbital path more closely. The other is an ion tail, made of charged particles that are pushed more directly by solar wind, creating a straighter line pointing away from the Sun. Both tails obey solar influence. Both are controlled by the star's radiation and magnetic field. This is textbook astronomy. This is what we teach in every planetary science course. This is what should be happening. But 3I Atlas is not doing this. Not entirely. Yes, it has material streaming from it. Yes, there's a coma. But the structure that's appearing in multiple observation images shows something else, two distinct extensions that run perpendicular to each other, and crucially, perpendicular to the line connecting the object to our Sun. Imagine drawing a line from the Sun to the comet. Now imagine two more lines extending from the comet at right angles to that Sun-comet line. That's what we're seeing. That's the cross. And the scale is staggering. These aren't subtle features you need enhancement algorithms to detect. The extensions reach across distances that would span the space between Earth and the Moon multiple times over. We're talking about structures that stretch for millions of kilometers. If you could somehow stand at one end of the cross and look toward the other, you'd be staring across a gulf that would take light several seconds to traverse. This isn't a small anomaly. This isn't a minor deviation from expected behavior. This is a massive, obvious, geometric structure hanging in space behind an object that has no business creating geometric structures. The images that revealed this pattern clearly came from stacked observations in November, multiple exposures taken over time and combined to bring out faint details. This is standard practice in astronomy. When you're looking at dim objects, you take many photos and layer them together, effectively increasing your total exposure time and revealing features that would be invisible in a single shot. The technique is sound. Astronomers use it constantly. But when they applied it to 3i Atlas, they got something nobody expected. There it was, the X pattern, two lines crossing. And the first response from many scientists was exactly what you'd expect. Is this an artifact? When you stack images of a moving object over time, could you create the appearance of a cross even if one doesn't really exist in space? Could the observation method itself be generating this geometry? That's a fair question. It deserves investigation. But here's the problem. When you analyze the individual images before stacking, you still see hints of this structure. When you look at observations from different telescopes, from different angles, at different times, the perpendicular extensions keep showing up. Independent observation teams are seeing the same thing. This isn't one telescope having a glitch. This isn't one dataset being misinterpreted. This is a consistent feature appearing across multiple observation methods and facilities. So, if it's real, if there really are two extensions projecting at right angles to the Sun object line, then what's causing it? This is where the explanations start to get interesting, and where scientists begin to disagree. The most conservative explanation focuses on rotation. Comets spin. As they spin, if they have active jets shooting material from their nucleus, those jets can sweep across space like a sprinkler head. Imagine a comet rotating rapidly, with two jets on opposite sides of its nucleus. As it spins, those jets trace out structures. If the rotation is fast enough, and if the ejection velocity is high enough, you could potentially create extended features that don't simply follow the Sun's influence. But here's where that explanation gets tricky. To create perpendicular extensions, to create that cross pattern, you'd need the jets to be oriented in very specific ways relative to the rotation axis. You'd need the ejection velocities to be high enough that the material travels far before solar radiation starts dominating its trajectory. And you'd need the geometry to remain stable enough over multiple observation periods that we keep seeing the same cross structure. Some researchers have calculated that you'd need ejection velocities between 200 and 500 meters per second to create the observed features. That's fast. That's much faster than typical cometary outgassing. Normal comets eject material at tens of meters per second, maybe occasionally over 100 in particularly active regions. But hundreds of meters per second? That suggests something unusually energetic happening inside 3i Atlas. It suggests processes that aren't fully understood, or conditions that are extreme, even by cometary standards. And there's another detail that makes the rotation explanation uncomfortable. The cross pattern appears quite symmetric. Both extensions seem similar in length and brightness. If this were purely a rotation effect with random jets, you'd expect more asymmetry, more chaos. Nature isn't usually this neat. Natural processes create messy results, but what we're seeing looks organized. It looks structured. It looks, and this is the word that makes scientists nervous, designed. Loeb has pointed to this apparent organization and suggested something that most of his colleagues find too speculative. He proposes that we might be looking at trails of ejected objects, not just gas and dust. He suggests that 3i Atlas might have expelled solid material, perhaps fragments, perhaps something else in specific directions. And what we're seeing is the debris trail left behind. If that were the case, the perpendicular geometry could indicate that whatever mechanism ejected this material did so in a controlled fashion firing material at right angles to the Sun-object line for reasons we don't understand. Jason Wright, an astronomer at Penn State, has been more measured in his response. He's pointed out that high-velocity jets could indeed create these patterns through natural processes, but he's also acknowledged that the observations are puzzling and deserve careful analysis. He hasn't dismissed the anomaly. He hasn't waved it away as nothing. He said what good scientists should say. We need more data. We need better observations. We need to understand the full picture before jumping to conclusions. But here's what nobody disputes. What we're seeing is unusual. The cross pattern is real, not an illusion. And whether it's caused by exotic rotation dynamics, high-velocity ejection, observation effects, or something we haven't even theorized yet. 3. I-Atlas is not behaving like a typical comet. It's an interstellar object, something that formed around a different star, traveled through the cosmic void, and entered our system, carrying whatever strange properties its origin environment gave it. We don't know what conditions exist in other star systems. We don't know what kinds of ices, what mineral compositions, what volatiles might be present in objects formed in different regions of the galaxy. We're looking at a visitor from an alien environment, and we're surprised when it doesn't behave exactly like the local comets we're used to. Maybe the surprise is our mistake. Maybe we've been assuming that comets everywhere follow the same rules, that objects formed in different stellar neighborhoods, with different radiation histories and different chemical compositions, will act just like the comets born in our solar system's outer reaches. Maybe what we're really learning from 3i Atlas is that the universe is more diverse than our models account for, that nature has more tricks than we've catalogued. But that still doesn't answer the central question. Why a cross? Why perpendicular extensions? Why this specific geometry? If this is natural variation, why does it look so organized? And why, of all the shapes that random processes could create, did this interstellar visitor happen to paint something in space that humans immediately recognize as a symbol? I'm not suggesting intent. I'm not claiming this is a message. But I am saying that when nature hands you something that looks this deliberate, that follows geometric rules this precisely, you have to stop and ask uncomfortable questions. You have to be willing to say, I don't know, and mean it. You have to resist the urge to force this observation into a comfortable box just because the alternative that we're missing something fundamental is unsettling. So how do scientists explain this? What theories are they actually working with? And why has the United Nations decided that this particular moment, right now, while this cross pattern is visible and while 3i Atlas is still bright enough to study, is the perfect time to launch a global tracking campaign? Let me show you where the scientific debate currently stands. In science, disagreement is healthy. It's the friction that generates progress. When researchers look at the same data and reach different conclusions, that's not a failure of the scientific method, it's the method working exactly as intended. Competing hypotheses, rigorous testing, evidence accumulation. Eventually, one explanation proves more accurate, or a new framework emerges that reconciles the competing views. This is how science advances. This is how we move from confusion to understanding. But with 3i Atlas and its impossible cross pattern, the disagreement reveals something deeper than just differing interpretations of data. It reveals a fundamental tension in how we approach the unknown. Do we stretch our existing models to accommodate new observations, no matter how awkward the fit? Or do we acknowledge when something falls outside our current framework and admit we might need entirely new concepts to explain it? The mainstream scientific position on the X pattern is essentially this. It's natural, but it's complex. High-velocity outgassing combined with rapid rotation and specific nucleus geometry could produce perpendicular extensions. The stacking of images over time might emphasize features that look more organized than they actually are in real-time observation. The apparent symmetry might be partially an observation artifact, partially a result of specific viewing angles from Earth. Given enough time, enough modeling, enough data, we'll find a conventional explanation that doesn't require invoking anything beyond known cometry physics. This isn't a stupid position. It's not scientists being stubborn or closed-minded. It's them following a principle that has served science well for centuries. Extraordinary claims require extraordinary evidence. When you see something unusual, first exhaust all conventional explanations before considering unconventional ones. The history of science is full of apparent anomalies that turned out to have perfectly natural explanations once we understood them better. The spiral nebulae that looked like clouds of gas, turned out to be entire galaxies once our instruments improved. The pulsing radio signals that briefly seemed artificial turned out to be rotating neutron stars. Nature is weird enough without inventing additional weirdness. But then, there's R.V. Loeb's position. And you have to understand, Loeb isn't some fringe figure making wild claims from the internet. He was chair of Harvard's astronomy department. He's published hundreds of papers. He's respected, credentialed, deeply embedded in mainstream astrophysics. He's also willing to ask questions that make his colleagues uncomfortable, and that willingness has made him controversial. When Loeb looks at the 3I Atlas cross pattern, he sees something that doesn't easily fit the conventional explanations. He sees extensions that are too symmetric, too perpendicular, too organized to be simply random outgassing shaped by rotation. He calculates the ejection velocities that would be required and finds them unusually high. He notes the precise right-angle geometry relative to the Sun object line, and he suggests carefully, with appropriate scientific caution, that we might be looking at something more than just a comet behaving oddly. His specific hypothesis involves ejected objects, not gas and dust streaming out in jets, but solid material, perhaps fragments, perhaps something else being expelled from the nucleus in specific directions. If that were happening, the trails left by these ejected objects could create the linear features we're seeing. And if the ejection were happening in a controlled manner, if there was some mechanism inside 3I Atlas that was firing material at right angles to the Sun object line, that could explain the perpendicular geometry. Now, Loeb is careful not to say this is artificial. He's not claiming we're looking at a spacecraft or a probe or anything built by intelligence. He's simply pointing out that the observations don't fit comfortably into our current models of natural cometary behavior, and we should be open to mechanisms we haven't considered. Maybe there are natural processes that can create controlled ejection. Maybe certain nucleus structures or internal pressure dynamics can produce these effects. But we won't figure it out if we immediately dismiss anything that doesn't match our preconceptions. Jason Wright, another respected astrophysicist, has taken a position somewhere between these poles. He's acknowledged that the observations are genuinely puzzling. He's pointed out that high-velocity outgassing could potentially explain some of what we're seeing, but he's also noted that the symmetry and geometry raise legitimate questions. His approach has been to say, let's gather more data. Let's run more simulations. Let's model this properly before deciding we know the answer. This is the scientific divide right now, not a screaming match, but a genuine disagreement about how to interpret observations that don't fit neatly into existing categories. And underneath that disagreement is a deeper question. How much do we really know about interstellar objects? We've observed exactly 2 confirmed visitors from beyond our solar system. Oumuamua, with its strange elongated shape and mysterious acceleration, and now 3I Atlas, with its cross-pattern and high-velocity ejections. 2 objects, 2 mysteries. That's not a large sample size. That's barely enough to start forming patterns, let alone drawing firm conclusions about how these objects typically behave. Maybe what we're learning is that typical doesn't apply. Maybe interstellar space is full of diverse objects, with wildly varying properties depending on where they formed, what their composition is, what kind of star system birthed them. Maybe our solar system's comets and asteroids are actually the weird ones, adapted to the specific conditions of our particular stellar neighborhood, and visitors from elsewhere naturally look strange to us because they're playing by different rules. Or maybe 3I Atlas really is unusual even by interstellar standards. Maybe we're watching something rare, something that only happens under specific circumstances we don't yet understand. Maybe in 1,000 years, when humanity has observed hundreds of interstellar objects, 3I Atlas will still stand out as that weird one that created a cross pattern, and nobody ever fully explained why. The truth is, we don't know. And admitting that, really admitting it, not as a placeholder before claiming certainty, but as a genuine acknowledgement of the limits of current understanding, is harder than it sounds. Scientists are trained to find answers. They're rewarded for solving puzzles, for reducing uncertainty, for building models that predict and explain. But sometimes the most honest thing you can say is, this doesn't fit, and I don't know why. What makes the current moment so charged is that the window for answers is closing. Every day, 3I Atlas gets dimmer as it moves farther from both the Sun and Earth. Every day, it becomes harder to observe, harder to study, harder to gather the data that might resolve these competing interpretations. The telescopes are pointed at it now. Observations are being made. Data is accumulating, but there's a clock ticking, and everyone involved can hear it. And that urgency, that sense that we might miss something critical if we don't act quickly enough, is exactly what motivated the United Nations to do something unusual. Something that, on the surface, seems routine, but when you look at the timing, raises its own set of questions. Let me show you what I mean. On November 27th, the United Nations Office for Outer Space Affairs, in coordination with the International Asteroid Warning Network, initiated what they called a planetary defense observation campaign targeting 3I Atlas. The campaign was scheduled to run for 2 months, through the end of January, involving observatories and research institutions around the globe in a coordinated effort to track, observe, and characterize this interstellar visitor. The official reason given was straightforward. This is a practice exercise. Planetary defense requires international cooperation. If a dangerous object were ever heading toward Earth, we'd need observatories worldwide to work together seamlessly, sharing data, coordinating observations, tracking the threat accurately. And since 3I, Atlas poses no danger but is bright enough to observe and interesting enough to study, it makes a perfect practice target. This is the 8th such exercise conducted by the international planetary defense community. It's part of an ongoing effort to prepare for potential future threats. That all sounds perfectly reasonable, sensible even. Planetary defense is important. Practice exercises are necessary. Using an interesting but harmless object as a test case is smart resource utilization. Nothing about this should raise eyebrows, except for the timing. The observation campaign was announced just as the clearest evidence of the cross pattern was emerging. Just as stacked images from November were revealing the full extent of those perpendicular extensions. Just as scientific papers were beginning to circulate discussing the anomalous geometry. Just as debates were heating up in the research community about what we're actually seeing. Is that a coincidence? Probably, most likely. The campaign had to be scheduled at some point, and 3I Atlas is leaving the inner solar system, so the window for bright observation was limited. If you're going to run a tracking exercise on this object, late November through January is the logical timeframe. The decision was likely made weeks or months earlier through normal bureaucratic channels involving multiple international partners. The fact that it aligned with the emergence of the cross pattern is probably just chance. But here's what makes the timing interesting. The United Nations and international space agencies don't typically run 2-month intensive tracking campaigns on objects that pose zero threat. When they identify a potentially hazardous asteroid, yes, absolutely, resources are mobilized, observations are coordinated, trajectories are refined. That's what planetary defense systems are designed to do. But for objects that are clearly not on a collision course, for comets passing through the system with well-understood orbits, the level of international coordination is usually much less intensive. So why this object? Why this level of attention? The official answer is that it's interstellar, and any opportunity to study an interstellar object is scientifically valuable. That's true, the research value is enormous, but there are other scientifically valuable objects out there that don't get 2-month global observation campaigns. There are other comets, other asteroids, other phenomena that would benefit from coordinated international study. What makes 3I Atlas special enough to warrant this level of organized attention right now? Maybe it's the combination of factors. It's interstellar. It's bright enough to study effectively. It's leaving soon, so this is the last chance. It's showing unusual features that deserve investigation. Put all of that together, and you have a compelling case for intensive observation. The UN campaign makes sense within that framework. But I also want you to consider another possibility. What if the scientists advising these international bodies saw the preliminary data on the cross pattern and realized we're looking at something genuinely anomalous? What if they recognized that this might be one of the most important observation opportunities in planetary science this decade, and they wanted to make absolutely sure we didn't waste it? What if the planetary defense exercise framing is partly bureaucratic convenience, a way to mobilize resources and international cooperation quickly without having to publicly say, we don't know what we're looking at, and we need every telescope available pointed at this thing before it's too late? I'm speculating now. I'm reading between lines. But institutions move slowly. Getting international cooperation takes time. Getting multiple observatories to coordinate their schedules, share data, work toward common observation goals that doesn't happen overnight. The fact that this campaign came together so quickly, so comprehensively, right as the most puzzling features of 3I Atlas were becoming apparent, suggests to me that someone, somewhere, recognized the urgency. What exactly are they tracking? The official goals of the campaign include refining the object's trajectory, characterizing its composition through spectroscopy, monitoring its activity level as it moves away from the Sun, and testing the coordination mechanisms that would be used in a real planetary defense scenario. All of that is legitimate. All of that provides valuable scientific data and operational experience. But they're also watching that cross pattern. They're analyzing those perpendicular extensions. They're gathering high-resolution data that might finally explain what's creating that impossible geometry. They're documenting everything about this object while they still can, because in a few weeks, 3I Atlas will be too dim to study effectively. It will fade into the background of distant stars and drift back into interstellar space, taking its mysteries with it. This is humanity's chance. This is the window. And the United Nations, along with observatories around the world, is making sure we don't squander it. Whether you believe the cross pattern is a natural but poorly understood phenomenon, or whether you suspect something stranger is happening, everyone agrees on one thing. We need data. We need observations. We need to capture everything we can about this object before it's gone. And that urgency extends beyond government agencies. Individual researchers are scrambling for telescope time. Private observatories are contributing data. Amateur astronomers with sophisticated equipment are adding their observations to the pool. There's a sense in the astronomy community that we're racing against the clock, that something important is happening right now, and the cost of missing it would be measured not just in lost scientific knowledge, but in decades of wondering what we might have learned if we just looked a little closer. But the real race isn't just about looking. It's about looking with the right instruments, at the right wavelengths, with the right sensitivity to capture information that might answer the questions this object has raised. And that's where the most advanced telescopes humanity has ever built enter the picture. Let me show you what's happening at the cutting edge of this investigation. There's a window closing, not in months, but in weeks, maybe days for certain types of observations. 3I Atlas is dimming as it moves away from both the Sun and Earth, and there's a hard physical limit to how faint an object can be before even our most powerful telescopes can no longer gather useful data. We're approaching that limit, fast. Right now, the James Webb Space Telescope is turning its unprecedented infrared capabilities toward 3I Atlas. Webb, the most powerful space telescope ever built, can see in wavelengths invisible to human eyes and most ground-based telescopes. It can detect faint heat signatures, analyze chemical compositions through spectroscopy, and resolve details that would be impossible to capture from Earth's surface. If anything can reveal what's actually happening inside and around 3I Atlas, it's Webb. The observations were scheduled for December, during the narrow window when the object is still bright enough for Webb to gather high-quality spectra, but after perihelion, when the most dramatic changes should be visible. Scientists want to understand what this object is made of. They want to see what gases are being released. They want to know if the chemical composition matches what we see in solar system comets, or if there are signatures of a different stellar environment, different formation conditions, different elemental abundances, and they want to understand those perpendicular extensions. Webb's resolution and sensitivity might reveal whether those features are truly structural, actual streams of material in space, or whether they're artifacts of how we've been observing the object. If they're real, Webb might show us fine details. Are they continuous streams? Are they fragmented? Are they made of dust, ice, or something else? Do they show internal structure that could hint at the ejection mechanism? But Webb isn't alone in this race. The Hubble Space Telescope, still operational after decades in orbit, is also targeting 3I Atlas with its ultraviolet spectroscopy capabilities. UV observations can reveal things infrared can't. They can detect specific ions, specific molecules that only show up in ultraviolet wavelengths. Hubble is looking at the hydrogen envelope around the comet, the way ultraviolet light from the sun interacts with outgassing material, the fingerprints of chemical processes happening in the coma. There's particular interest in something called the sulfur-to-oxygen ratio. Different types of comets show different ratios of these elements. Solar system comets formed in specific temperature ranges at specific distances from the sun show characteristic sulfur and oxygen abundances. If 3I Atlas shows a very different ratio, it might indicate formation in a different stellar environment with different conditions. That would tell us something profound about the chemistry of other star systems, about whether planet formation follows similar rules everywhere, or if there's huge diversity we haven't accounted for. And then there are ground-based observatories. The big professional telescopes Keck, Gemini, the Very Large Telescope Array in Chile, are all contributing observations. They're tracking position, monitoring brightness, capturing images in different wavelengths, building up a comprehensive dataset that spans the entire spectrum from radio waves through visible light to infrared and ultraviolet. Why this full-spectrum approach? Because different wavelengths reveal different information. Radio observations might detect molecular emissions invisible in other wavelengths. Infrared reveals heat and dust. Visible light shows the overall structure. Ultraviolet catches high-energy processes. You need all of it to build a complete picture, but there's a desperate quality to this effort. Everyone involved knows that every day that passes makes the object harder to observe. Brightness is dropping. Signal-to-noise ratios are getting worse. The amount of telescope time needed to gather useful data increases as the object dims. There's a point, approaching soon, where it simply won't be feasible to continue. The object will be there, still moving through space, but it will be too faint to study effectively. This is our chance. This is the moment. And it's not just about the cross pattern. Scientists want to understand everything about 3i Atlas because opportunities like this are vanishingly rare. We might not see another interstellar visitor this bright, this well-observed, this amenable to study for years, maybe decades. When Oumuamua passed through, we missed most of our observation window. It was already leaving when we realized what it was. By the time telescopes could focus on it, it was nearly gone. We got some data, enough to know it was weird, but not enough to really understand it. We're not making that mistake with 3i Atlas. The astronomy community mobilized early. Observation started while it was still approaching. We've tracked it through perihelion. We're watching it leave. The dataset being assembled is comprehensive in a way that the Oumuamua data never was. And that means when papers are published, when analysis is complete, when researchers have time to really dig into what we've captured, we'll have a much clearer picture of what interstellar visitors actually look like. Or we'll have a much clearer picture of how little we understand about what's possible. Because here's the thing about gathering more data. Sometimes it resolves mysteries, and sometimes it deepens them. Sometimes better observations lead to clear answers, and sometimes they reveal that the situation is even stranger than initial data suggested. What if Webb's infrared spectroscopy shows chemical compositions that don't match any known solar system comet? What if the sulfur-to-oxygen ratio is wildly different, suggesting formation conditions unlike anything in our planetary system's history? What if high-resolution imaging reveals that those perpendicular extensions have internal structure, patterns within patterns, organization that's hard to explain through random outgassing? I'm not predicting that will happen. I'm simply pointing out that we're in a moment of genuine uncertainty. The data is being gathered right now. Analysis will take weeks, maybe months, papers will be published, debates will continue. And there's a real possibility that what we learn makes 3i Atlas even more mysterious than it already is. But there's also a possibility, maybe more likely, that careful observation and analysis will provide natural explanations for everything we're seeing, that the cross pattern will turn out to be a complex but ultimately understandable result of rotation, high-velocity jets, and observation geometry, that the chemical composition will show some differences from solar system comets, but nothing that can't be explained by formation in a different stellar neighborhood, that in a year, this will be a fascinating case study in cometary physics, but not a paradigm-shifting mystery. Either outcome is valuable. Either way, we learn. We expand our knowledge of how these objects behave, what processes drive their activity, what diversity exists in the galaxy. We get better at recognizing interstellar visitors when they appear. We refine our models. We improve our observation techniques. This is science working as intended, gathering data, testing hypotheses, moving toward better understanding. But while the telescopes track and the data accumulates, there's another layer to this story that deserves attention. Because the cross pattern isn't just a scientific puzzle, it's also a collection of competing interpretations, each trying to explain how nature could create something so geometrically precise. Let me walk you through what researchers are actually proposing, because the range of theories reveals just how unsettled this question really is. When something unusual appears in space, scientists do what they're trained to do. They propose mechanisms. They build models. They test whether existing physics can produce the observed effects. And with the 3I Atlas cross pattern, that process has generated several competing theories, each with its own strengths and weaknesses. The rotation theory is probably the most conservative. It proposes that 3I Atlas has an irregularly shaped nucleus with active jets regions where gas and dust are escaping into space. If the nucleus is rotating rapidly, and if these jets are positioned on opposite sides or at specific angles, the rotation would cause the jets to sweep through space like spinning sprinkler heads. Over time, as material is continuously ejected and pushed outward, this sweeping motion could trace out extended structures. For this to create a cross pattern with perpendicular lines, you'd need the rotation axis and jet positions to align just right. The jets would have to be ejecting material at high velocity so it travels far before solar radiation takes over. And the observation geometry from Earth would need to be such that we're seeing this structure from an angle that emphasizes the perpendicular nature. It's not impossible. Comets do rotate. Jets do exist. Geometry does matter in how we perceive structures from our specific vantage point. But the theory requires several conditions to be met simultaneously, and it doesn't fully explain why the pattern appears so symmetric and organized. Natural rotation with random jets usually creates messier results. Then, there's the high-velocity ejection theory. This focuses on the sheer speed at which material seems to be leaving. 3I Atlas. Calculations suggest ejection velocities that are much higher than typical cometary outgassing. If material is being thrown out at hundreds of meters per second, it would travel much farther before solar forces dominate, potentially creating the extended features we're observing. But what would cause such high-velocity ejection? One possibility is subsurface pressure buildup. If volatile ices are vaporizing beneath the surface, pressure could accumulate until it explosively releases, firing material outward at high speed. This happens with some solar system comets during outburst events, but to sustain the features we're seeing would require repeated or continuous high-velocity ejection, which is less common. Another possibility involves the neckline phenomenon. Some comets have a neck region where two lobes of the nucleus meet. If 3I Atlas has a similar structure, outgassing from the neck region could create specific patterns different from poles or equatorial jets. The geometry of material escaping from a neck could potentially produce perpendicular features depending on the nucleus shape and rotation. But again, this requires specific conditions. The nucleus would need to be bilobed. The neck would need to be active. The orientation would need to be right. It's possible, but it's building a model that fits the observation rather than predicting the observation from first principles. There's also the observation artifact theory. This suggests that what we're seeing isn't entirely real, or rather, it's an emphasis of features that exist but are being made to look more prominent and geometric than they actually are by how we're observing them. When you stack images over time, when you use enhancement algorithms to bring out faint details, you can sometimes create or enhance patterns that weren't obvious in individual observations. This is worth considering seriously. Artifact analysis is a crucial part of astronomy. You have to know your instruments, know your processing methods, know what kinds of false patterns they can create. And there's precedent for features that look significant in processed images, but turned out to be less dramatic in careful analysis. However, multiple teams using different observation methods and different processing techniques are seeing this cross pattern. It's not one artifact in one dataset. It's a consistent feature across multiple independent observations. That makes the pure artifact explanation less likely, though it could be that part of what we're seeing is enhanced by observation methods. And then there's Avi Loeb's ejected objects theory. Instead of gas and dust streaming out in jets, Loeb suggests we might be looking at trails left by solid material fragments, perhaps that were ejected from the nucleus in specific directions. If such ejection occurred perpendicular to the Sun object line, if it happened with enough force that the ejected objects traveled far, their trails could create the linear features we're observing. This theory raises obvious questions. What would cause such directional ejection? What mechanism inside a comet could fire material at right angles to solar influence? Loeb doesn't claim to have all the answers, but he points out that we don't fully understand the internal structure and dynamics of interstellar objects. Maybe there are natural processes we haven't encountered in solar system comets. Maybe certain nucleus compositions or internal pressures can create these effects. Or maybe, and Loeb carefully leaves this possibility open without claiming it's likely there's something about 3I Atlas that isn't entirely natural, Not that it's artificial, not that it's built by intelligence, but that it might have undergone processes or experienced conditions that produced features we wouldn't see in a purely natural comet that formed and evolved without any unusual influences. This is where the conversation gets uncomfortable for many scientists. Because once you start suggesting that something might not be entirely natural, you're opening a door to speculation that can quickly become uncontrolled. You're inviting questions about extraterrestrial intelligence, about objects being more than they appear, about possibilities that sound like science fiction. But Loeb's position is more nuanced than that. He's not claiming 3i Atlas is a spacecraft. He's simply saying that when we see something that doesn't fit our models, we shouldn't immediately force it into those models just because the alternative makes us uncomfortable. We should follow the evidence. We should stay open to explanations we haven't considered. And we should admit when we genuinely don't know. The truth is, all of these theories have problems. The rotation theory requires very specific geometric conditions. The high-velocity ejection theory needs an energy source that's not well explained. The observation artifact theory doesn't account for multiple independent confirmations. The ejected objects theory proposes mechanisms that aren't well understood or proven. So where does that leave us? With a mystery, with an observation that doesn't have a clear, universally accepted explanation, with multiple research teams looking at the same data and reaching different conclusions about what it means. And with the clock ticking as the object that created this pattern dims and fades, taking the opportunity for better observations with it. Maybe the upcoming data from JWST and Hubble will resolve this. Maybe high-resolution spectroscopy will reveal chemical signatures or physical processes that make one of these theories clearly correct. Maybe we'll look back in a year and wonder why this ever seemed mysterious once we understood the full picture. Or maybe we won't. Maybe this will be one of those observations that remains ambiguous, where multiple interpretations are possible, and we never quite gather enough data to definitively choose between them. Space is full of such mysteries, phenomena we've observed, but never fully explained, questions that remain open decades after the initial discovery. But even if we don't get a definitive answer about the cross pattern, even if 3i Atlas keeps some of its secrets as it returns to interstellar space, this entire episode has value, because it's teaching us something important about how we approach the unknown. It's revealing our assumptions, it's showing us where our models might be incomplete, and it's reminding us that the universe is under no obligation to make sense to us on our schedule. And that leads to a question that matters beyond the technical details of jets and rotation and observation geometry. This leads to the question of what this all means for us, for humanity, for our understanding of our place in the cosmos, for how we think about the possibility that the universe holds surprises we haven't imagined. Let me be clear about something right from the start. 3i Atlas poses zero threat to Earth, none. Its trajectory is well understood and it's not coming anywhere near our planet. This isn't a disaster scenario. This isn't a warning in the sense of impending danger. Whatever that cross pattern means, whatever's creating it, it's not something that should keep you up at night worrying about cosmic threats. But it should make you think. It should make you wonder. Because what we're witnessing with this interstellar visitor is a direct confrontation between human understanding and cosmic reality. And we're learning that reality doesn't always match our expectations. Science is supposed to be humble. It's supposed to be provisional, always open to revision, always willing to say we were wrong when new evidence appears. But in practice, science can become comfortable. When models work well for decades, when predictions keep matching observations, there's a natural tendency to assume we've basically figured things out. We might not know everything, but we know the important parts. We know the rules. We know how nature behaves. And then something like 3i Atlas appears and creates a pattern that shouldn't exist according to those rules. And suddenly we're reminded how much we're still guessing. How many assumptions we've built into our models. How much of the universe remains genuinely mysterious. This is valuable. This is important. Because science advances fastest, not when it confirms what we already believe, but when it encounters phenomena that don't fit. Every major revolution in scientific understanding came from observations that broke the existing framework. The perihelion precession of Mercury that didn't match Newtonian gravity and led to relativity. The black-body radiation spectrum that classical physics couldn't explain and led to quantum mechanics. The galactic rotation curves that didn't match visible matter and led to dark matter theories. Anomalies drive progress. Mysteries push us forward. And 3i Atlas, whether or not its cross pattern ever gets fully explained, is serving that function right now. It's pushing researchers to think more carefully about cometary dynamics. It's motivating better observation techniques. It's forcing theorists to model scenarios they hadn't considered. It's doing exactly what anomalous observations should do. It's making us better at science. But there's something else happening here that extends beyond pure scientific value. There's a human element, a moment of collective wonder. How often do we get that in our modern, explained, quantified world? How often does something appear that genuinely surprises us, that makes us look up at the night sky and remember that we're on a small planet orbiting an average star in a galaxy full of things we've never seen and might never understand? We've gotten used to space being predictable. We track asteroids with precision. We calculate orbits decades in advance. We send probes to distant worlds, and they arrive exactly when we planned. Space has become, in a sense, domesticated, mapped, known. And then an object from another star system passes through, does something weird, and suddenly space is mysterious again. Suddenly there are questions without easy answers. Suddenly we're reminded that the cosmos is bigger and stranger than our comfortable models account for. That reminder has value. It keeps us curious. It keeps us asking questions. It keeps us funding telescopes and space missions and research programs, because there's still so much to learn. If space were fully understood, fully explained, fully predictable, why would we keep looking? But as long as mysteries remain, as long as objects like 3i Atlas can surprise us, the drive to explore, to understand, to reach further remains alive. And there's something specifically poignant about this mystery being tied to an interstellar object. This isn't something from our neighborhood. This isn't a comet that formed in our solar system and follows rules we've studied for centuries. This is a visitor from elsewhere, from a region of space we might never reach, from a stellar environment we can only infer. It came here carrying whatever properties its origin gave it, and we're trying to understand it based on what we know from local examples. It's like trying to understand an animal from a distant continent based only on your knowledge of local wildlife. Some features will be familiar. Basic biology, basic physics applies everywhere. But some adaptations, some behaviors might be unique to that environment, shaped by conditions you've never experienced. You can learn from the familiar parts, but you have to stay open to the possibility that the unfamiliar parts represent real differences, not just variations on themes you already know. That's what we're doing with 3i Atlas. We're trying to understand a visitor from an alien environment, and we're discovering that our local rulebook might not be complete. Maybe comets from other star systems do things our comets don't. Maybe the chemical compositions, the internal structures, the outgassing dynamics can vary more than we thought. Maybe the universe is more diverse than our limited sample size prepared us for. And if that's true for comets, what else might it be true for? What other assumptions are we carrying into our models of how the universe works? What other surprises are waiting out there in the cosmic dark, in the regions we haven't observed, in the phenomena we haven't yet encountered? These aren't just abstract philosophical questions. They have practical implications. Every assumption we make limits what we're prepared to recognize. If you're convinced that all comets behave a certain way, you might miss important features of one that behaves differently. If you're sure that certain phenomena are impossible, you might dismiss observations that indicate they're happening. The history of science is full of missed discoveries because researchers weren't looking for something, weren't expecting something, had convinced themselves that certain possibilities were off the table. And the solution isn't to believe everything, to accept every wild claim, to throw out careful skepticism. The solution is to maintain a balance, rigorous analysis, combined with genuine openness to the unexpected. Question everything, but don't dismiss anything without good reason. That's the mindset 3i Atlas is teaching us to adopt. Look at the data carefully, consider conventional explanations thoroughly, but don't force observations into frameworks they don't fit just because the alternative is uncertain. Be willing to say, "I don't know," and mean it. Be willing to leave questions open while we gather more evidence. Because sometimes the most honest answer science can give is that we need more time, more data, more analysis before we can be confident in our understanding. And there's no shame in that. There's actually great strength in that, the strength to resist premature closure, to live with uncertainty, to keep investigating, even when the answer isn't immediately clear. And that brings us to the questions that remain. Because as much as we've learned about 3i Atlas, as much data as we've gathered, as much analysis as has been done, there are still fundamental things we don't understand about this object and its mysterious cross pattern. Let me walk you through what's still puzzling researchers, what observations still need explaining, what questions are keeping scientists engaged with this investigation, even as the object dims and fades. What actually creates the perpendicular geometry? This is the central question, and it remains genuinely open. We have theories: rotation, high-velocity ejection, observation effects, ejected objects, but none of them fully convincingly explains why those extensions run at right angles to the Sun object line. Why perpendicular? Why not 30 degrees off? Why not random directions? What mechanism produces such precise geometry? If it's rotation-driven, why is the pattern so symmetric? Natural rotation with random jets typically creates asymmetric, chaotic structures. But the cross pattern shows remarkable organization: two extensions of similar length and brightness, perpendicular to each other and to the Sun object line. That level of symmetry suggests either very specific nucleus geometry and jet positions, or some process we haven't identified that naturally produces organized output. What are the actual ejection velocities, and what's driving them? The calculations, suggesting hundreds of meters per second, are based on assumptions about how far material travels before solar influence dominates. But we don't have direct measurements. We don't know precisely how fast material is actually moving. And if those high velocities are real, what internal process is accelerating material to such speeds? Standard sublimation and gas pressure don't typically achieve those levels. Is there something unusual about 3I Atlas's composition? Something about how it formed? Something about pressures building up during its interstellar journey? What is this object actually made of? This is where the JWST and Hubble observations become crucial. We need detailed spectroscopy to understand the chemical composition. Is it mostly water ice like many solar system comets? Does it have different ratios of carbon dioxide, carbon monoxide, methane, ammonia? What about more complex organics? What about dust composition, silicates, metals, carbon compounds? And particularly important is that sulfur to oxygen ratio I mentioned earlier. Different formation conditions produce different elemental abundances. If 3I Atlas shows a ratio significantly different from solar system comets, it tells us something profound about where and how it formed. It tells us about the chemistry of its birth star system, about the temperature and pressure conditions in that protoplanetary disk, about whether the rules of planet and comet formation are universal or vary widely between stellar environments. Why did the cross pattern become most visible after perihelion? Comets change as they approach and pass the Sun. They heat up, increase activity, sometimes undergo outbursts or fragmentation. Did something specific happen to 3I Atlas around perihelion that triggered or enhanced whatever process creates the perpendicular extensions? Was it always doing this, and we just couldn't see it clearly until it got close enough? Or did proximity to the Sun activate something that wasn't active before? Are the extensions continuous streams, or are they fragmented? This matters for understanding the ejection mechanism. If it's continuous outgassing creating sustained jets, that implies one kind of process. If it's multiple discrete ejection events creating trails of fragments, that implies something different. High-resolution imaging might answer this, but we're at the limits of what even our best telescopes can resolve at the distances involved. How does 3I Atlas compare to Oumuamua? We have two confirmed interstellar visitors now. Oumuamua was weird elongated shape, strange acceleration, no visible coma or tail. 3I Atlas is also weird, but differently. It looks more like a comet, but it's creating this anomalous cross pattern. Are these two data points suggesting that interstellar objects are generally strange? Or are we just seeing the high variance tail of a distribution that includes lots of normal objects we haven't detected? What can we expect from future interstellar visitors? If we detect a third, fourth, fifth object from beyond our solar system, will they also show surprising features? Or will 3I Atlas and Oumuamua turn out to be the unusual ones, and most interstellar objects will be boringly normal? We can't know yet with a sample size of 2, but every future detection will either confirm or challenge the patterns we're starting to see. Will the cross pattern persist as the object moves away? Or will it fade, change shape, disappear entirely once solar influence decreases? Continued observation, as long as the object remains bright enough, will show us whether this is a stable feature or a temporary phenomenon tied to specific conditions near the Sun. What would closer observation reveal? We're observing 3i Atlas from Earth and Earth orbit, millions of kilometers away. What if we could send a probe? What if we had a spacecraft that could approach, could observe from different angles, could measure things directly instead of inferring them from distant spectroscopy? Unfortunately, interstellar visitors move fast, and we get almost no warning before they arrive. By the time we detect them, it's too late to launch a mission that could intercept. But future technology, future detection capabilities might change that. If we could spot incoming interstellar objects years in advance, we could potentially send probes to study them up close. And there's a bigger question underlying all of these specifics. How much diversity exists in the galaxy? We've only studied our own solar system in detail. We've only observed comets and asteroids that formed here, in this specific stellar environment, from the specific protoplanetary disk that gave birth to our sun and planets. But the galaxy is vast. There are hundreds of billions of stars, trillions of planets, countless comets and asteroids formed in wildly different conditions. How much variation is there in how these objects form, what they're made of, how they behave? Are the rules pretty consistent galaxy-wide, or is there enormous diversity? Does the type of star matter? Does a comet formed in a system around a red dwarf differ significantly from one formed around a sun-like star? Does the position in the galaxy matter? Do objects from the dense central regions differ from those in the sparse outer arms? We don't know. We've barely begun to sample the diversity of objects in our cosmic neighborhood. Every interstellar visitor that passes through gives us one more data point, one more example of what's out there. And as that sample grows, we'll start to understand the full range of possibilities, the full spectrum of what nature creates in different environments across the galaxy. But right now, we're still at the beginning. We're still surprised by each new visitor because we don't yet know what to expect. And that sense of surprise, that feeling of encountering something genuinely new, is both exciting and humbling. Exciting because discovery and mystery are what make science worth doing. Humbling because it reminds us how much we still have to learn. So where does all of this leave us? We've examined the impossible cross pattern. We've explored the competing theories. We've seen the urgent scramble to gather data before the observation window closes. We've acknowledged the questions that remain unanswered. What's the takeaway? What's the bottom line on 3i Atlas and its mysterious geometry? Let me bring this all together and show you why this matters, why you should care, and what happens next. Right now, somewhere in the darkness between Mars and Jupiter, growing dimmer with each passing day, an object from another star system is carrying a mystery away from us. We've watched it. We've photographed it. We've analyzed its light, measured its trajectory, tracked its movements. And we've seen it do something that shouldn't be possible, creating a cross pattern in space, a geometric structure stretching across distances that mock human comprehension, defying easy explanation, and challenging our understanding of how these visitors behave. In a few weeks, maybe a month, 3i Atlas will fade beyond what even our most powerful telescopes can effectively observe. It will still be there, still traveling, still carrying whatever strange properties its distant origin gave it, but we'll no longer be able to study it. We'll no longer be able to point our instruments at it and gather new data. The window will close, the opportunity will pass, and this interstellar visitor will return to the cosmic dark, taking some of its secrets with it. The data we've gathered will be analyzed for months, probably years. Papers will be published, debates will continue. Different research teams will propose different interpretations, will build different models, will argue for different mechanisms that might explain what we've seen. Some of those explanations will involve conventional physics rotation, high-velocity jets, observation geometry. Some will push at the boundaries of what we think we know about cometary dynamics and interstellar objects. And eventually, a consensus might emerge. Or it might not. We might look back at 3i Atlas as the object that taught us something new about how comets work, or we might remember it as one of those persistent mysteries that space occasionally hands us, phenomena we've documented but never quite fully understood. Either way, we've witnessed something remarkable. We've been alive during a moment when an object from beyond our solar system, from a place we'll probably never visit, passed through our cosmic neighborhood and showed us something we'd never seen before. That's not a small thing. In the long span of human history, in the brief window of time when we've had telescopes powerful enough to observe these visitors, we've been here for this. We've been watching. We've been paying attention. And that matters because the universe doesn't wait for us to be ready. It doesn't schedule its mysteries around our observation capabilities or our theoretical frameworks. Things happen whether we're watching or not, whether we're prepared to understand them or not. The fact that we're now capable of detecting these interstellar visitors, of gathering data, of asking meaningful questions about what we're seeing, that's an achievement. That's something our ancestors couldn't do. That's something future generations will build on. Think about what we've learned just from two objects. Oumuamua taught us that interstellar visitors can be strange, elongated, accelerating, unlike the local comets we're used to. 3i Atlas is teaching us that strangeness can take different forms, geometric patterns, perpendicular extensions, behaviors that challenge our models, 2 data points, 2 mysteries, and a growing understanding that the galaxy is probably full of surprises we haven't encountered yet. Every future detection will add to that understanding. Every new visitor will either confirm the patterns we're seeing or reveal new variations. We're building a catalogue of what's out there, one object at a time, and eventually, maybe not in our lifetimes, but eventually that catalogue will be comprehensive enough that we'll understand the full diversity of objects travelling between stars. But we're not there yet. We're still in the early days, still surprised by each new example, still figuring out what questions to ask. And that's okay. That's how exploration works. You start with ignorance, encounter mysteries, gather data, build understanding, and gradually expand the boundaries of what you know. 3i Atlas is part of that process. It's a chapter in the larger story of humanity learning to read the cosmos, learning to interpret what we see when we look beyond our immediate neighborhood, learning what's normal and what's anomalous in the vast space between stars. And you've been part of this. You've taken the time to understand what's happening. You've engaged with the mystery. You've thought about the implications, the questions, the possibilities. That engagement matters. Science isn't just something that happens in laboratories and observatories. It's something that happens when people care enough to ask questions, to seek understanding, to grapple with uncertainty. So, what happens now? The observations continue as long as the object remains visible. The analysis proceeds as data gets processed. The debates unfold as researchers compare interpretations. And somewhere in the next few months, papers will start appearing that present formal scientific conclusions about what we've seen. You can follow that process. You can watch as the scientific understanding develops. You can engage with the ongoing investigation, not as a passive observer, but as someone who cares about the answers, who's invested in the questions, who recognizes that this matters. Hit the like button if this mystery fascinates you the way it fascinates me. Drop a comment and tell me what you think. Are you convinced by the conventional explanations, or do you suspect something stranger is happening with 3i Atlas? Subscribe to stay updated as new data emerges, as new analysis is published, as this story continues to unfold. Because this isn't over. The observation window might be closing, but the investigation continues. And beyond this specific object, beyond this particular mystery, there's a larger journey happening. Humanity is learning to look outward, to understand our cosmic context, to recognize that we're part of something much bigger than our single planet or our single star system. Every mystery we encounter, every anomaly that challenges our understanding, every question that doesn't have an easy answer, these are opportunities. Opportunities to learn, to grow, to expand the boundaries of human knowledge. 3i Atlas has given us one of those opportunities. A visitor from the stars created an impossible pattern in space, and we were here to see it. That cross pattern, stretching across millions of kilometers, those perpendicular lines defying easy explanation. That geometric precision appearing where nature should be chaotic. It's all a reminder that the universe is deeper, stranger, more mysterious than our comfortable models suggest. And that's not something to fear, that's something to celebrate. Because a universe that can still surprise us, that can still show us things we didn't expect, that can still make us wonder and question and seek, that's a universe worth exploring. The mystery continues, the questions remain, the investigation proceeds, and we're all watching together as this chapter of the cosmic story unfolds. Welcome to the moment when an interstellar visitor painted a cross in space and humanity paid attention. Welcome to the beginning of understanding what that means. Welcome to the mystery. Stay curious, stay engaged, and keep looking up. Because the cosmos has more surprises waiting, and the next one might be even stranger than what we're seeing now. The universe is vast, the unknown is infinite, and somewhere out there, between the stars, the next mystery is already heading our way.